So, hello everybody, and thank you very much for your interest in my talk. I would like to thank also to the organizers for giving me this possibility to introduce my work here. So my title is quite a long title. I will pick up some keywords from this title during my talk. So the main aim is whole body motion generation, and especially I'm interested in quite dynamic motions, how to generate dynamic motions. And the secondary aim is how to realize these dynamic motions using a controller. So I hope you will be interested in our control structure that is not only for dynamic motions, also for tasks like multi-contact control and so on in real time. So our point is to generate all these motions and these tasks in real time. So this is the outline of my talk. First, I'll give a brief self-introduction, and during this self-introduction, I'll try to explain the idea, where we got this idea about the distribution of momentum. Then I will go on with a hypothesis that is used in motor control of human motions, and that humans use synergies, muscle synergies, kinematic synergies, to generate the motion, various motions. Because I want to make use of this hypothesis. Then I will give you some overview of emergent motion generation in robotics, because this is not a new problem in robotics, but maybe some of you know it, maybe some of you are not so familiar, but it's important to think of this and why emergent motion generation is so important. After this, I will introduce the momentum equilibrium principle, which actually is well known in balance control, in humanoid balance control with respect to the linear motion, but it has not been considered with respect or in-depth considered in respect to angular motion. Okay, I will move on then with to explain our multitask control design approach, and finally give you, I have prepared a number of results, mainly simulations for balance control while standing or while walking, as well as a number of acrobatic performances generated with our controller. So from my studies, actually, when you see here the dates, it's 40 years ago, a long time ago, I started with my PhD study. So during this 40 years, I have picked up here for this talk 5 topics. One is kinematic redundancy, one is parallel link manipulators, another one is about the free-floating space robotics. Then I will talk something about singularities, so the so-called singularity consistent path tracking, because this is also important in whole body motion generation. And finally, about the main topic of today's talk, about motion generation control for humanoid robots. So at the start of my PhD, in our lab, we had actually 1980s. It was the time when industrial robots were hot topic. So in my lab, there was an industrial robot, and we had 6 degrees of freedom arm. But luckily, or it was at that time, it was not so lucky for me, but it was mounted in a slider that was also servo controlled. So I had a manipulator of 7 servo controlled axes, and I have to. My task was to solve the inverse kinematics. Now it's very easy. But we came up with, I came up with this equation here, and as you can see, it's quite familiar now, but at that time it was the first paper where it was published. So you have nested null spaces. One is the Jacobian null space, and another one is the remaining degrees of freedom null space. So later, this method became known as the task of priority method. So after my PhD studies, we started working on a topic about actually parallel topology manipulator. My colleague, Dr. Sotiro, found out something about these parallel manipulators. They were not very well familiar in the robotics community at that time. And we designed a controller for force control and made a simulation for this packing hole assembly, which was also a hot topics for industrial robots, packing hole assembly. So further on, a bit faster forward, in the 80s, I moved to Japan, and there was an idea to walk to free-floating space robots were quite a hot topic at that time, in its Professor Metani's laboratory. So I came up with the idea to put on a redundant, kinematically redundant arm on a satellite base and to see what happens. So this was the first time that I came across this equation. This is the angular momentum equation, which has a 0 on the right side, because in zero gravity you have the conservation of angular momentum. So this equation has two components, one for angular momentum for the satellite base and one for the manipulator. And the coefficient matrix is the coupling inertia matrix for joint velocity, actually. And I was looking for a similar solution like in redundant robots. So find out that the null space of this coupling inertia matrix can be used, like in this equation on the right side. This null space later we call the reaction null space. So I will explain how we can use this reaction null space. And this work, 1992 actually, this gives you two different examples of a free-floating robot. One on the left side is when the anti-vector trajectory is constrained within this reaction null space, the null space of the coupling inertia matrix. In that case, there is no attitude deviation of the satellite base, which is quite important. In the conventional way, if you don't have this, if you don't use this reaction null space, you have a deviation in this satellite base. And the deviation of the satellite base is very unpleasant because you have a communication link, you have an antenna, and if the antenna changes orientation, you lose this link to the Earth-based control station. So it's very unpleasant. Actually, we were lucky later on, 10 years later on, there was an experiment in space of a real space robot with the Japanese space agency. And we were lucky to try this reaction null space-based approach. And it went quite successful. So with this project, it was called ETS-7 mission, actually. There was a satellite base and a manipulator, and there was a smaller satellite that was attached. And then it was supposed to be detached and then retrieved with the manipulator arm. So there was a docking problem. The manipulator arm had to dock with this sub-satellite to retrieve it. This was, of course, a very nicely designed because the approach and the docking was very, very slow so that you don't have impact. But similar scenarios when you have to deal with space debris, so a lot of flying objects are over there, you don't want to get involved. So if you want to try to get this debris with the manipulator arm, like this, you have an impact. So when you have an impact, what you've got is, during the impact, there is no control. So you've got just a jump in the joint velocities and a jump in the satellite base angular velocity. And as is usually the case, you have here high gear ratios in space. It's not so nice like Patrick reported. We don't have this type of nice gear ratio set. But if you have this, that means the joints are nearly locked. Then you have the behavior of the system like a composite rigid body. If you have a composite rigid body, that means delta theta dot is minimized, almost zero, and delta omega b is maximum. So you have a lot of change of attitude in the satellite. As I mentioned, this is not desirable. What we came up with this idea is to work on post-impact control instead, because we cannot do anything during the impact, which is very short phenomenon. So for post-impact, we proposed base angular momentum damping. We rewrote this angular momentum conservation on the left. We rewrote it in terms of joint accelerations in order to deal with have a higher bandwidth response. And we used, like here, feedback gain for joint damping, joint velocity damping. So in this way, it is possible to swiftly transfer the momentum to the arm. Why is this needed? Because if you swiftly transfer the momentum to the arm, the base is not so disturbed like in this. But anyway, so you transfer the momentum to the arm, so the arm starts moving very fast, which is eventually the joint will hit the limits, which is also not a problem. So what we have to do, we have to get rid of this energy. This is a little bit, I'm explaining about this because a little bit different than in Earth-based robotics, which everybody is doing now in humanoids, but we can learn, I have learned from this, about this momentum distribution. What is this? This momentum transfer. So the manipulator arm is moving fast. So what we have to do, we have to bring back the momentum to transfer it again to the base. Why? But we do it slowly because it's a matter of time. So we do it slowly. In this way, we can use the reaction wheels. There are reaction wheels in the base and store the energy, impact energy in the reaction wheel. So it's a momentum transfer and energy transfer. If you store this in the reaction wheels, later you can use then the jet thrusters to get rid of this eventually. So this is one example. I hope I could explain to you why this momentum transfer is so important. And it is similar. We have similar studies in human body control about such momentum transfer. Imagine tennis serve. There is a study about tennis serve. So if you serve, you have to generate angular momentum and you have to, the player has to transfer it to the racket so that it has to hit the ball in an optimal way. So this is also such an example of momentum transfer I'm going to talk about today. Okay, so another topic about motion generation, which I found very important in humanoid robotics as well, is the problem of kinematic singularities. So 1995, there was this publication, I made this publication, and the method to deal with so-called ordinary singularities. I'll explain in short what that means. So the method is, I think you will understand first in this equation number 3, you have, this is the forward kinematics function, and you have an end effector path that is parameterized by parameter alpha. So I wrote this equation in this type of with end effector parameterization, and you see that this is not directly dependent on time, so it is autonomous dynamical system in the form. And if you take the first derivatives, like here in equation 5, you get a vector field equation. And based on this vector field equation, on the right side I have a 0. Here I can put an error. So this becomes like here on the right side. So the difference between forward kinematics and the trajectory, the parameterized trajectory, desired and-tip trajectory. And this is a vector field zero dynamics control, which turns out to be quite successful in dealing with this type of ordinary singularities. In order to understand this, maybe you can think of a very simple example of a 2-arm manipulator, and the end link is required to move along a straight line. And on this left and right, it hits this workspace boundary, and this is singular configuration. And you can think of this system as a closed chain slider crank mechanism of 1 degree of freedom, like this. So we don't, when you think of this, we don't have any singularity. This singularity simply disappear from the equation. So the manipulator can come here and then it goes back by reconfiguring itself. We have implemented this with the real parallel link robot in 1994. It's a hexatype, all rotational joints parallel link robot. So the end link, the traveling plate, is following a straight line, and in the same time, the legs of the robot are reconfiguring. So like elbow, I said legs, but maybe hands. So it's elbow left, elbow right, and they change in this way. So the kinematic singularities simply disappear. This is used, they used to call it assembly mode in parallel robotics, because in order to change that configuration, it was thought that you have to disassembly the mechanism and to assemble it in the, let's say, from the right elbow to left elbow configuration assembly mode. So now with this control method, you don't have to think about assembly mode. So how is this related to humanoid robots? We have implemented this method for humanoid robots. On the right side, right down, you see some creepy motions we have in this way. So the legs are following, sliding on the floor, and in the same time, they are reconfiguring. And also the arms, you can do this with the arms. So some sort of creepy motions. So for some people don't like these creepy motions, and maybe they are useful. I hear there is a superhuman or a superhumanoid session, maybe in the humanoids, this year's humanoids. So maybe you can use it as an example of a superhuman or superhumanoids. But since we have the uncanny valley problem, you can go on the left side. You can stop the motion, of course, of the singularity itself. And we have implemented also this for straight leg walking in 2006. This is just a static walk, and it is very clumsy. We have it now also in dynamic walk. So I finished this, and just to summarize or sum up, so my studies on humanoid robotics actually have three pillars, like kinematic redundancy for motion optimization, my studies on parallel link manipulators for force optimization, and the free-floating robot studies for angular momentum control. So kinematic redundancy I can use for multi-body control, parallel link manipulators for multi-contact control, and the angular momentum for enhanced balance control. Now, about the studies on motion generation, whole body motion generation. Actually, I was thinking all the time during these 40 years and so about kinematic redundancy, and there, of course, many methods have been introduced, pseudo-inverse, the most straightforward one, or some weighted pseudo-inverse, or some null spaces, and so on. But since we have to deal with a humanoid robot, it has a human-like body. So how to make this whole body motion generation? What is the? And I came to this conclusion that we should expect human-like movements. And since we expect human-like movements, the people expect human-like movements, the conventional redundancy resolution doesn't work. We have to look into the way humans generate their motions. So motion capture is not an elegant solution, of course. So let me go on in this outline with the human motion generation hypothesis. And it goes way back to Hugh Links-Jackson, an English neurologist. Way back in 1889, he published this article, which he has very famous. He's saying that the central nervous system knows nothing about muscles. It only knows movements. So what does it mean? It means muscles. I think it good fits also with Patrick's presentation that you have a sort of passive dynamics, or muscles play their role mainly. You can name them passive dynamics. But the central nervous system, it generates commands that relate only to movements. So this is a clear call for a task-based approach. Depending on the task, the central nervous system, there is a hypothesis, it generates some movements. And it does not generate the movements for each degree of freedom. What this guy, this is Nikolai Bernstein. It's in the beginning of the Soviet era. He was tasked with to study the motion of the humans, especially for labor. They wanted to become very skillful laborers. So on the left side, you see his task, one task he considered this was hammering and chisel. And this was a very simple task because the arm moves fairly in one plane and the hammer is in one plane. So he could easily analyze it with these cyclograms. He used something like a motion capture, you say in the middle of this movie, I found. And so he could analyze, and he found out that there is a problem because the hammer, when the guy who was hammering, the laborer, he was trained very well such that the hammer always hits on the same place and always uses the same trajectory. But on the other hand, the arm, the motion in the segments of the arm was different from cycle to cycle. So he called this the degree of freedom problem. It is known now as the Bernstein's degree of freedom problem. So he was wondering, how does the central nervous system deal with this degree of freedom problem? By elimination of unnecessary degrees of freedom, it was rejected. This is not. By optimization. Our brain does not have time to optimization. So he came up with this hypothesis, and that there are synergies, or we call it the motor field. And he proposed a formulation in terms of coordination, motion coordination, these synergies. So he came also with this maxima that the most important function of the brain is the organization of movement. This is amazing, I think. So in the field of humanoid robotics, it's so important to think of this, that it's most important, think of the brain, and we have to understand how this works. So there are simple synergies already known and used in humanoid robotics. Like on the left side, you have this, in the sagittal plane, the ankle strategy, when you have a slight push in the back and then you stronger push, you have this hip strategy, and the stronger push, you have the step strategy. And on the right side, there is a similar, or in the lateral plane, you have, again, depending on the push, you have different synergies. And factory, the synergy analysis in the field of biomechanics and physical therapy are used a lot of, and these are some recent studies. So especially Professor Latash is very known in these studies. One thing which I want to relate to our control design is the Bernstein's description of synergy. He said that the coordinational net of the motor field is non-rectilinear. So we have some nonlinear stuff, and it oscillates like a cobweb in the wind. So this oscillation, however, does not destroy the topological relationship. So topological, there is some topology in this. So he said either of zero order or the first, perhaps even higher orders, he thinks. So this sounds like an almost autonomous dynamical system. You have a topology there. And then the task synergies you can view as motions on a slightly time-varying manifold in motor or in joint space. And the variations are used to compensate internal and external errors. So like this hammering task, the hypothesis is that each time the hammer is trajectory is the same, but the arm compensates for some errors, like small internal errors or possibly some small disturbances and so on. So this topic, actually, this is confirmed. We have a manifold it's called the uncontrolled manifold or the UCM concept. And this is hot topic because we have a very recent paper, the uncontrolled manifold. So the manifold is determined via its tangent bundle in differential geometry. And that is with the help of the null space of the task Jacobian. And because it is null space, there is an idempotency property which preserves the topological structure. So this fits very nicely in the hypothesis. So I will come back to this later in design and our control design. Now let me go to a brief overview because the time is quite advancing. Overview of emergent motion generation that are used in robotics. The synergies have been addressed in robotics. In the 1970s, especially Vukobratovic studies, mainly in relation to a human robot. So walking gate synthesis, actually. They use walking gate synthesis. They talk about synergetic rays, that we have to use some types of synergy in this, but it was not very clearly formalized. Also in the 70s, later in my studies in redundancy, I used a lot, I refer to this paper of Alain Lijoie in France, and he was talking about synergy when resolving the redundancy of a 7 degrees of freedom arm. Much later, so in the 70s, there was some talk about synergies, but then there was nothing. And after the millennium change, we have now some synergies started appearing. For example, these are some in the area of grasping. So because grasping, you have also so many degrees of freedom in the fingers, you have to, they found out that we have to use some type of synergies to get, and this later, this third paper has some formal definition of a grasping synergy. And we have also, as I mentioned, the synergy and balance. The ankle and hip strategy first appeared 2002 in this paper. Later in Goswami and Kalem 2004, we had implemented this with HOPE2 robot using the reaction null space. We use the reaction null space for the hip synergy. And a nice, very nice paper is this one, which has also a formal definition of a synergy. I will give you an example of this use of the reaction null space we made 2016, some 5 years ago. We made this type of experiment. So we asked, we put this guy on a slider without any damping. And we asked him to make just a squat, and trying not to move the slider as much as possible. But as you can see, this was not possible because there was an imperfect movement. Maybe we did not go so far, but if you try very hard and you learn this synergy, maybe you'll get very perfect and almost keep the slider without any movement. But I think this is very difficult because there is some time delay in our central nervous system. It's not about 200 milliseconds. It's very important, this time delay, for dealing with this imperfect. So when I apply the reaction null space on the right side, you see we can get reaction less movement, perfect reaction and movements. And that is what I want to aim in motion generation, to design perfect dynamic motions as much as possible for a given task, because this is a task-dependent issue. Let me, So I want to talk about emergent movement synergies and explain with a simple example, again with this 2R manipulator example, to show you that what is about this simple synergies, that we want to generate a complex motion with a simple command. This is the main point. And we found out that if you have this type of 2R manipulator with equal link lengths and they are overlapping, then you have a bifurcation singularity, because you don't know if you apply a command that pulls down or along a reference path that pulls down in the same, it's aligned with the links. So there is no way that this system knows, the robot knows how to move. It stays like this. But if you have a small deviation from the perfect, let's say 180 degrees in the second joint, if you have a very small, infinitely small deviation, then we know that the system will start moving either right or left. In my case, it's right. So it results, if you apply this command, it results first in a pure rotation of the links. So the end link does not move, almost no more. You cannot see with the BR that it moves, but it, because 90 degrees rotation, when it becomes orthogonal to the command, then the end link, the end effector, the end keeper starts tracking the reference path, and you have stage 2 tracking the reference. So this is an example with the same command, and it generates a quite a complex motion. I'll show you. We applied this to a humanoid robot, so you can see on the left side what I have. I have a commanded COM motion velocity upward. Just a simple command for the COM motion upward. And on the left side, I did not constrain the motion of the arms. So you can see when the legs are extended, they go to singularity, and the arms continue moving, because with this motion, the center COM command is still valid. So it can move up with this motion. On the right side, you can see that I constrain the hands not to move, but because the redundancy of the arms, you have 1 degree redundancy each arm. So they they change the configuration from elbow down to elbow up with the same command. So this is an example how you can generate this type of motions. Okay, so there are some emergent movement synergies used. These are well, I hope you know them very well. In humanoid robotics, like Goswami and Hare, you have this about spin angular momentum relation. In DeLassa, in animation, and some recently worked also. We have as arm swinging, as also the work of Patrick in 2013. You have upper body emergent motion, jumping and kicking, and so on. And recent work which Patrick reported now about the Cheetah tree robot, I think. This is a work related to this one. Okay, so let me go on with momentum equilibrium principle. Now, I think that everybody would agree that angular momentum plays an important role in enhanced balance control, and it has been linked now I went very fast through this overview of the emergent motion generation, but the arm swinging, there was a toe off, emergent toe off, and also hip shoulder counter rotation. These are examples of such emergent generation. So the open problem is, however, how to distribute this desired angular momentum among the body segments. So you have desired angular, but how to distribute it here? So there you can get some emergent, like arm swinging. It's fairly simple. You can get it, and toe off also, not so difficult. But how to distribute it, more complex motions. So I start on with, again, with the angular momentum equation. On the right side, you have the angular momentum. I have rewritten this in terms of centroidal angular momentum. And therefore, here in front of the base or base link, we have the Serbia and the composite rigid body inertia tensor. This is the coupling inertia, the same. So you have something which I will call system angular momentum, it's a centroidal angular momentum. So I have a CRB angular momentum component, and I have a coupling angular momentum component. Now I can solve for the joint velocities using, for example, the pseudo-inverse of H omega, and get when I know the LC reference and omega B reference. So I will use this type of model to apply this. So this is a robot model. It has a torso joint with 3 degrees of freedom. This is important to generate very human-like motions. So using this pseudo-inverse is it the best way to distribute? Now, let me go a little bit further. I can simplify and rewrite this angular momentum equation in terms of angular velocity. So I use it like this by defining j omega. So I use the inverse of the CRB tensor. It's always positive definite. And I define the omega c system angular velocity. Okay, so it's actually, these are equal equations, but it's a little bit easier to understand. So I have CRB angular velocity component, coupling angular velocity component are the two components. Now let me talk about the momentum equilibrium. So we use this idea for inverted pendulum, and balance control is very known, ZMP manipulation-based balance control. And this is a relative motion phenomenon. What about this in the angular momentum? So we can rewrite the angular momentum, angular velocity equation in this way, put the coupling velocity, angular velocity on the left side. On the right side, you have a finite difference. So you have a CRB motion, we call this the relative angular velocity, actually. So you have pure motion and a CRB motion component. And this is the dynamic equilibrium for angular momentum. Coupling angular momentum, angular velocity is always in equilibrium with the relative angular velocity. So we use this in controller design. And we can use it for balance stabilization task, feedback, or we can use it for zero relative angular velocity by using a motion in the reaction null space, balancing on a pole task. There is no feedback at all. So let me show you this. So if you see here, this is a feedback. We use a feedback here for using a feedback from the sensor for the angular deviation of the foot. You get an impact, a very strong impact. So the robot is first in conventional control, conventional balance control. And after the impact, so if conventional balance control continues, you can see here the omega f is the indicator for destabilization. So it goes very straight up exponentially. It will be destabilized if you don't use nice control. So we have here relative angular velocity, zero dynamic stabilization in this case, and it can swiftly destabilize, and then the motion will be recovered. So this is an example of graph stabilization recovery. And on the other hand, we can put the robot on a rotation on a pole. It's a point contact, actually. This is an unstable posture, initial. And we can use just a feed forward RNA stabilization to stabilize. So the arms are free to move, and even it can forward bend. You can give a forward bend desired, it destabilizes, and immediately after this, it stabilizes again. So it's so like a super stability for this. Okay, so let me go on with our motion control design. So what we do is we use this omega b and omega c, this relative angular velocity based angular momentum design, and we also use conventional COM design component and end-link component, which includes the Jacobian and also includes the contact maps. And on the right side, this is the desired spatial velocity of all the end links. So in order to make a nice design, we have to make some, we have to remove, for example, the motion in the hands. We have to make it through motion, so use this selective matrices. These have, you can select either selection in the COM motion or the base motion or the angular momentum motion or the joint motions of the feet, the torso, or the arms. So depending on the task, appropriate task components are removed. As much as possible, I want to remove. So the solution in terms of angular acceleration is like this. And I use simple control laws like this, feed forward plus PD, damping, For walking, we use DCM-based damping, and so on. This is also for this. We use also for the CRNS-based control and admissible angular centroidal angular momentum control. We use a weighted generalized inverse and the null space component we have here. So the null space component is just for postural control, as usual. This is nothing new. The weighting matrix is something more involved, but also not so much new. So we use two components for the weights. One is inertia-based, and one is range of motion-based, joint limit-based. So we can combine them, superimpose them by using appropriate setting with CRB inertia components for the base and with components from the complex inertia components. And we use here a threshold, which is determined like this, with this constant is empirically determined. So we have this type of motion. And you can see that if you compare pseudo-inverse based angular momentum distribution with weight-based angular momentum distribution, the arm motion is much more than this. So you can see also this is with some graphs in this. I will go very fast over it. It seems my PowerPoint is, sorry, this is the time is going on. I'm sorry, I have to, my PowerPoint was. Okay, so this is our control, which we designed. It has these components for the control laws, hand wrenches, and so on. Okay, so because it's time, I will go very fast over this and go show you some results. So we have disturbance accommodation in single stance. This is reaction in single stance. This is when you have on the shoulder. This is when you have in the lateral plane. These are controls which we designed for walking, like arm swinging and combination with pelvis and arm swinging, also with toe rotation. This is how you can superimpose synergies, walking with sounds, arm swinging, a very large impact. This is a blind stepping on impact, and this is standing back flips. I'm sorry. So this is a standing back flips idea. I have no time now to show it. It's going some saturation of this. Let me see if I can again try it. Out of time, I guess. So this is a backflip which we generated. Okay, I'll go over this data. This is different types of gain. So these are variations in the parameters. This is a standing long jump simulation. And we have a professional-like simulation where the feet go to the ground, and amateur-like when you have with the feet are touching, and then you have toe rotation. In the end, we can simulate also like this. We have acrobatic others like standing front tuck and vertical jump. And currently working on this type of simulation. So this is my conclusion. I'm running out of time. So thank you so much for your patience.
Many thanks for your nice presentation. It's really great to know that some of the well-known equations are perhaps even older than me. Thank you very much. Are there any questions? Okay, so if not, maybe we can thank you, Nenchev, again for your nice presentation. I'm really impressed by the backflip. I think that is, if we can put it on the real robots, that would be very, very impressive. And but the simulation already paved solid stone to this direction.
Thank you.
Thank you very much.